Well, good afternoon, everybody. And from what I see on my screen here, everybody includes Aaron and Andrew and Dana and John and Richard and Tucker, and maybe one more person to come. And when we have a group this size, and here came somebody else. Let's see, David, I guess, just joined. So we have our uh, 7 people, and I think there's maybe one more to come. But if we could, when I have a group this small, it means we can get a little more close and personal. And there's our number 8 person. So we're all here. Um, if we could start alphabetically at the top of the list with Aaron Harris. Aaron, if you would just briefly, what branch of engineering are you, and what specific job assignment? And what I'm interested in is the level of involvement in PV at this point, so it gives me an idea of where I need to keep the level of the presentation. So, Aaron, would you just turn on your mic and tell us a little bit about yourself, your background, and what you're doing right now, other than, I mean, when you're not at this webinar. You go ahead, click your microphone, unmute. Can I do that? Nope, you gotta do it yourself. If you don't have a microphone, if you want to just type it into the, let's see, do we have a, you can type it into the chat box, I guess. Normally, I like to save the chat box for communication with the host in case there are any technical issues. But let's see, Tucker, I'm not sure we have the option to unmute. Oh, okay. And I guess you don't have that option. So what the host is saying is please use the chat box. So that works fine too. If you just type in the chat box, we'll read it as it comes up. And your name will appear, I think, automatically. So just your discipline and your particular area of practice. What are you doing right now? Are you in MEP? Are you in photovoltaic, structural, civil? Just quickly type that in. While you're doing that, I guess I'm not unmuted. So my background is electrical engineering. I taught electrical engineering for 35 years and then retired almost 20 years ago. And I'm now involved with a former student who has an engineering business in, okay, an MEP, solar team. Okay, inverter retrofit. Great. Okay, Maria. Glad to hear that. And so you have some idea what we'll be talking about today, maybe a lot of idea. Let's see, what else have we got here? Maria was in. In any case, I'm working for a former student who has become got his PE, and we design solar systems, mostly residential, but some commercial. And we've designed somewhere in the neighborhood 15,000 or more systems in the last 5 years. So we've had a little bit of experience there. My job is to check them before they go out, make sure that they're hopefully clean. Okay, and Tucker, don't apologize. Natural gas is pretty important too. That's where most of our electricity comes from right now. Forensic engine. Oh, okay. Very interesting. Yeah. Okay, you got your own install. And okay, good. Sounds good. That's David. And I guess everybody can probably read what's going on in the chat box. And Aaron's a civil and structural, which is important for PV. We sure don't like those things to blow away, and we don't like them to leak either, for that matter. You're civil, site development, and you're interested in PV personal use. Good. We'll learn a lot about that today. And you can only read your messages. Okay, Maria. All right, well, let's get going. There's a lot of material here, so and we don't want to keep anybody too long. We are going to be getting pretty serious about design, but in order to do a good design, it helps to understand what you're using, your materials. So it's one thing I'm noticing in the education all over the world now. People are just telling you how to do it, but they don't normally give you an idea of why you're doing what you're doing and how the thing really works. We've had that experience with our electric range, all kinds of repair work and stuff. People just come in, look at their phone and do what it tells them to do. They don't have to think anymore. And my personal opinion here is it is pretty important to still retain that ability to have some human intelligence involved in the process. And that's what we're going to be emphasizing today is using human intelligence in order to design things that use a lot of these things that may have been designed with a lot of help from some useful uh, artificial intelligence type stuff. So here we go. One of the questions is this stuff still too expensive? We're going to answer that question. Um, and here's part of the answer. Move something out of the way. There we go. If you go back to 1975, photovoltaics, well, they were hobby things or space things because it was over $100 a watt. Whereas if we're back here in 2024, we're down in the neighborhood of less than 30 cents a watt, which means the cost has come down by a factor of more than 500, and that doesn't even account for inflation. If you account for inflation, it'd be down a whole lot more than that. And but what's interesting is to take a look at what this has done in terms of the amount of photovoltaics out there. But in terms of cost, uh, with the cost of photovoltaics, what it is right now, if we use the so-called levelized cost of electricity comparison by source, and this is 2027 is the estimate of what the U.S. Energy Information Administration is estimating the cost will be, then levelized cost of electricity is simply adding up all costs associated with the cost of electricity, which means the materials, acquisition, construction, the operation, the fuel, the maintenance, and the final decommissioning of the source. Add all those dollars up, and the final decommissioning may have positive or negative value. If you can sell your solar modules when you're done after 25 years or something, they still work. So maybe somebody wants to still buy them. So we might have yeah, that may be a benefit rather than a cost. Anyway, then you divide that by the total amount of electricity generated by the source over its lifetime. And you get, the numerator of the equation is in dollars, the denominator is in kilowatt hours, or we can convert it to cents per kilowatt hour. And if we convert these numbers to cents per kilowatt hour and apply them to a number of energy sources, this is what we see. Combined cycle dispatchable stuff, 3.75. That's pretty reasonable. Not half bad, given that we're paying 15 cents or so a kilowatt hour here in Florida. And that's, in some areas, that's cheap, although in TVA, that's expensive. But Tennessee Valley has got some dams that have been there for a long time. Onshore wind, 3.78. Standalone photovoltaics, 3.35. Whoa, how about that? For standalone. Hybrid PV, this is PV with storage, 5.47. In other words, PV that will power your occupancy 24/7, 5.47 cents per kilowatt hour, or in other words, solar with batteries. And residential PV at about 6 cents, and that because it's a little more complicated and a little more detailed, as we'll see. have to have special fire provision and things that you don't need with a large utility system. And so you can see that PV is right in there with the cost of other things. Geothermal 3.74, and natural gas is somewhere in that 5-cent region as well. So, but otherwise, and notice this does not include the so-called externalities that are associated, the smoke, the acid rain, the CO2, and so forth that might be associated with various sources. If we can assign a dollar value to those, then some of the prices go up a little bit. Simply because if you had to consider the increase in cost of insurance or something like that. So in any case, well, normally insurance would be part of the operating cost. So no, I'm sorry. Unfortunately, the bottom of my slide is has the closed captions going across it, so I can't read it. But anyway, I think maybe you can read it. In any case, this is what EIA expects things to be in 2027. And this residential PV number one, it's important to recognize that this varies a lot. If you're doing PV in Miami, where some of your uplift pressures get in the neighborhood of 80 pounds per square foot or so, maybe even more. That's a little more expensive than in an area where your uplifts are in 20 pounds per square foot, and you don't have to fasten them down quite as extensively. So, and for that matter, you can have modules that have a lower pressure rating. So the residential 6 cents is a nominal average value for around the country. A little higher in Florida, a little lower in other places, but averages out around 6. So therefore, we have our economic justification because if you borrow the money, it's going to start paying for itself right away because your payback on the loan will probably be less than the difference between what you used to pay on your PV and what you're now, or what you used to pay on your utility bill and what you're paying now on your utility bill. So your savings will generally exceed your payments back on the loan. And that goes on for a length of the loan, maybe 10, 12, 15 years or so. And after that, then it's all yours, whatever savings is goes to you, and inflation, whatever might be the case. So all these numbers, they don't include a whole lot of time or value of money. Now, if we look at the energy return on investment for PV, because that's something people talk about, they say, oh my goodness, you didn't count the fact that it takes energy to make this stuff. But then again, it takes energy, no matter what your energy source is, to turn it into a source that can actually make energy rather than just be a bunch of iron or steel or crude oil. So if we look at, but this is still a legitimate concern on any kind of an energy source, including something like ethanol from corn, where the amount of energy it takes to make kilowatt hours worth of, or let's say a BTU's worth of energy on corn is almost equal to the amount you get back from it. So your energy return on investment on some sources isn't all that good. So let's take a look and see what it is here on photovoltaics. All right, it's just simply the ratio of the energy produced over the cell lifetime to the energy used to manufacture the cells. And in 2024, this number is somewhere between 10 and 45, and it depends on the technology and specifically the location, because some places make more electricity than others using the same technology. So the EPBT, the energy payback time, is roughly 3 years. Okay, which means that you paid back that initial energy investment in 3 years, and the rest of it you're making energy, and that means you can use that energy now to create additional energy, and the sun is your lending source. And as long as you do it within the next 4.5 billion years, you're pretty much can consider that that sun is going to be there to provide your energy source. So one reason the prices are falling is because the energy return on investment is increasing. In other words, it's taking less energy to manufacture these cells than it used to, and therefore it takes less time for them to pay for themselves. Okay? Because the production is becoming more efficient. The cells themselves are becoming more efficient. A mere 10 years ago, 15% efficiency was great. Now 21, 22% efficiency is pretty good. And that is not just a 7% increase. When you go increase from 15 to 22, that's a 50% increase, meaning on your rooftop, you can generate 50% more energy now than you could even 10 years ago. So these are a very positive indicator. The inverters, the balance of system energy costs, they are also decreasing. Not only are their costs decreasing, but their warranties are improving. A lot of the microinverters now in use are warranted for the life of the modules, which is 25-year warranty. That's pretty good. So not only that, new technologies are coming online. Coming online pretty fast. So moving on, what kind of types of PV systems are there? Standalone, looks something like this. And yes, it is possible to generate electricity with photovoltaics in Alaska. This is the entrance to the exit glacier on the Kenai Peninsula. And, or maybe it's the exit. This car looks like it's coming into the entrance, though. The car going down the road the other direction will be at the exit. And then there are grid connected. Standalone simply means it's not connected to the grid. Do you make the electricity, you store some in batteries, or you don't even have to necessarily do that on some of the systems. And it gives you the electricity you need to operate the entrance station at a national park, or a cabin, or wherever else you might want it. Then there's the grid connected stuff. And as of the year 2000, there was more grid connected being constructed than standalone. But before that, standalone was the main thing, and it was a cost issue. So now I got the grid connected stuff. This some of you, if you're maybe from New York, you might recognize this up in Tupper Lake at the Nature Center up there. This was there way back, 15 years or so ago. It was one of the really modern installations at the time, one of the nicest ones I'd seen. And I couldn't resist walking around to take a picture of it. So grid connected simply means you make electricity, you use whatever you can of what you make, and anything left, you sell it back to the grid. As some examples, here's one in Nevada. This is at an entrance to a national park. At the park headquarters. This would be a standalone. Here is another standalone in Utah, weather station. Another standalone, Wyoming. Sign, big game crossing. And for the next 5 miles, you better watch out for that big game. So here's some standalone stuff, but that's not it. If you go up to Massachusetts, you can see some rooftop PV. And why Massachusetts? Well, you can kind of tell this is Massachusetts. They don't want that snow to settle on the roofs. They've got pretty steep, like 45-degree slopes here. But then that's good, because if they're looking south at 45 degrees, that's almost optimal. But notice, assuming those are looking south, there's also some looking west. And notice on this other roof, even though these modules may not be pointing south, as was almost the necessity 20 years ago, just because of cost. Now, because of the price going down, it's even justifiable here in South Florida to have modules facing north. And we're going to talk about some more detail about that as we go through. Yellowknife, Northwest Territories, one of my favorite pictures. When I went by this, I couldn't resist taking a picture of this. Um, you know, not a whole lot of code restrictions up there. And so we'll just install these things, whatever it takes to capture some of that electricity. Some of these along the Yellowknife River, where this one was, there were a few others that had some wind and some solar both. And these are undoubtedly battery backup systems too. But you can see there is utility coming in off there to the left as well. So a little of each. And so they're all over. Big ones, commercial rooftop, utility scale, the big fields. So that's a lot of PV out there, and it's growing like crazy. Sun information helps to know what the sun does. The peak sun intensity is 1,000 watts per square meter at sea level when the sun is directly overhead. All right, when it's not directly overhead, it has to go through a little more what's called air mass. And the more atmosphere it passes through, the atmosphere absorbs some of that heat. Because at the above the atmosphere, the sun intensity is 1,367 watts per square meter. So we're losing about 30% to the atmosphere, which absorbs it, reflects it, does a lot of stuff, but it interferes with that which actually reaches the surface of the Earth on a nice sunny day. But 1,000 watts per square meter, that's not too bad. You can do a lot with that, as you'll see. Depending on technology, about 20% can be converted to electricity, and some are, we've got seeing some 22% modules now. They're pretty, really, the theoretical upper limit on plain silicon is somewhere in the 27% range. So 22 out of 27 is about as good as you can get. And there's some nice quantum physics rules that back that up, and we're not going to do quantum physics today, but I have to ask you to take my word for that. And let's see. Oh, I guess since you can't unmute, I'll be watching my screen for anybody who has anything they want to add through the chat. So don't hesitate to ask questions. That's the whole idea of a live presentation, is to allow for feedback. The annual conversion range is typically between 1,000 and 2,000 kilowatt hours per kilowatt per year. So if you've got a kilowatt system on your roof, chances are you're going to make this many kilowatt hours of energy per year for each of those kilowatts. And it depends on where you are and what is the orientation of those modules specifically. And the National Renewable Energy Labs has a fantastic program that you can get for free by simply Googling NREL, and it's called the, SAM, Systems Advisory Model. And so if you just Google NREL SAM, you can download it for free. And it's a lot of fun to play with. And if you get bored with whatever you're watching on TV, you can simulate what a solar system might make if you put it on your own roof, for example, because you just give it all the parameters. What's the slope of the roof? What direction are you facing? And where specifically are you located? And if you can tell it what equipment you're using, it even takes into account the temperature, the weather condition, and the efficiency of the equipment, depending on the level at which it's operating. So very sophisticated program, and it's amazing that you can download it for all the thank you give them as your email address. And the only time they send you an email is when they've got a new update. So not a bad deal. I've been doing this now for, well, I don't know, a long time, 15 years or more. Something in the chat. Let's see what we got. Wind loading design, and also like better understand how strung together one. Oh, that's exactly what this is all about. So don't you worry, we'll be there. Spell the name of that program, please. National Renewable Energy Laboratories, NREL. And the name of the computer program is SAM, System Advisory Model, but they go by the acronym SAM. Okay, let's see, Maria there and David. Anything else? Okay, switch gear again. So that's okay. Yeah, so hopefully that answer, well, I didn't, the answer to the question is yes, you're going to get the answer in gory detail in just a moment. First thing, how do these modules work? Well, it's very interesting. If you plot the current versus the voltage versus the sun intensity, it's going to look like this. And this is pretty interesting stuff. It says basically the modules operate pretty much as a current source, that is at 1,000 watts per square meter sunlight intensity. This module is going to be putting out about 11.6 amperes all the way out to about 35 volts. Then the current starts going down as the voltage continues to rise, and at some point up here around 49.5 volts and 1,000 watts per square meter, you notice that there is no more current, only voltage. So there are four parameters that characterize the module. The short circuit current, and notice that if we have 0 volts across the module, if we face the sun and short out the two leads, the current is limited to 11.6 amps roughly in this module. If it's at 1,000 watts per square meter incidence on it. At 800 watts per square meter, then you're going to see less than that, but proportionately less. Now, there's some other tricks here too, because these parameters are also voltage or temperature dependent. But notice there is a point on this curve where the voltage times the current is a maximum value. That's called the maximum power point of the curve. So for this particular module, notice that that maximum power point occurs somewhere in the neighborhood of 42 volts. And depending on the intensity of the sunlight, somewhere between 0 and 1,000 watts per square meter. Okay? So therefore your current is going to be between 0 and 12 at pretty much the same maximum power voltage, as long as the temperature of the module remains constant. And that's problematic because it's likely that it won't. If the module is 20% efficient, that means some of the sunlight is reflected away, but the remaining 65% or so is likely going to be converted into heat, half of which radiates upward and half of which radiates downward. But then again, if you look at that, that means your roof doesn't, it runs a whole lot cooler because the module is blocking more than 60% of the heat that might otherwise shine directly on your roof. So that's a plus because your roof lasts longer. So anyway, this is an important characteristic of a module, and you have to match your modules with your inverters and your other equipment. So these numbers will tell you how many modules you can put in a string without overfilling the string. And we're going to come to that because we're going to do several design examples. Okay, so we have short circuit current, voltage, open circuit voltage, maximum power current, maximum power voltage. Okay, that's the four parameters they're mostly characterized by, but they also then are characterized by their various temperature coefficients for these different quantities. Now, here's how the power versus voltage curves look like, and this makes it a little more obvious where there's a maximum power voltage, and notice it's around 42 volts, but clearly power is current times voltage. So one of the important components of a solar system is called a maximum power point tracking circuit. And that's a very simple circuit. Well, it's a very, very elegant circuit if you think about it, that it draws current from the module and measures the voltage, multiplies it, and then tries a different amount of current, multiplies, tries it, and zeroes in on where that quantity is maximized. And these maximum power point trackers are roughly 99% efficient, so extremely efficient for staying on this maximum power point. All right, and this is the sort of thing people take for granted, but it is not particularly simple, but is incredibly reliable. And so most charge controllers, we'll call it a charge controller, but the charge controller function, the maximum power point function, is normally incorporated at the input side of the inverter itself. Okay? So, and depending on the inverter, and we'll look at a number of different kinds of inverters and how they do their maximum power point tracking or whatever. Okay, another important quantity is how the power of the module varies with temperature. And here you see at 25C, that's where the test is done in the lab. So this you can see is basically a 440 watt module at standard test conditions, but if you decrease it by 25 degrees C down to 32 Fahrenheit, then it's going to put out almost 500 watts. Of course, then sun is shining on it, it's going to make it warmer, and so it's kind of hard to get it that cold unless it's nighttime, but then it's kind of hard to get the sun to shine on it. So it's an interesting trade-off there. But see, if you go up to 75C, then your power output is down to about 375 watts, something like that. So fairly significant. So the idea is you want to try to run things as cool as possible. One way to do that is to have them stand off the roof a little bit so you get a little breeze underneath them to cool them down a bit. And that's one of the main reasons why PV systems are mounted off the roof rather than on the roof. Now, there are some PV shingles, and they get warmer, but they're a different technology, and their temperature dependence isn't quite as much, but also their overall efficiency is significantly lower than what we have for the silicon, which is why silicon makes up 96% essentially of today's market, crystalline silicon. Okay, so what do we got here? Notes. Maximum power decrease is about 0.36% per degree C, so you want to keep it cool. All right, these are just some background things that make you appreciate why certain things are done in the design. Now, what about the orientation? Well, let's look at Albany, New York. The optimal orientation in Albany is facing south at a 30-degree tilt. And your annual output is then at its maximum. On the other hand, if you're tilting 45 degrees instead of 30, you raise the tilt by 15 degrees, you only lose 1%. If you go flat, you lose 13%. Okay. If it's vertical, 67, so that means you lose 33%. So you maybe don't want to go vertical in Albany. On the other hand, at a much higher latitude, like in the Kenai Peninsula of Alaska, you go pretty close to vertical and you don't lose nearly that much. On the other hand, here in Florida, flat, you don't lose that full 13%. So you can see how the orientation and the tilt affect the output of the module with respect to the maximum output. And we're going all the way up to north at a 15-degree tilt, where even in an Albany, you can still get 71% of what you would get in the optimal tilt at 30 degrees. So what does that mean? It means you have to have 100 over 71 times more of them. It means your levelized cost of electricity goes up by that factor, and it's still less than the cost of utility electricity. So things are different now from the way they used to be. Nobody would ever have even imagined north-facing modules being financially attractive. Okay, so just some numbers to come in handy. Now, what are some of the options for grid connect? Well, there's straight grid connect, and all that simply is you make your DC electricity with your modules, you convert it to AC with an inverter, feed that AC any number of different places, but the first choice for the use of that electricity is the occupancy itself, and anything the occupancy does not use goes back to the grid. And that's it. And therefore, you can't do this unless you have an agreement with utility. Okay, So part of the installation is the utility interface agreement. And the utilities all have them. Some are 8 pages long, some are 1 page long, pretty straightforward. All depends on whose lawyers got paid the most. But as long as you meet certain requirements, then you must be allowed to connect to the grid. That requirement is the IEEE 1547 or UL 1741, which we'll go to in detail as we move through. All right, so in any case, the straight grid connect can sell back to the grid anything that's not used by the host of the system. Battery backup, grid connect, all of the above. But the other thing that happens with battery backup circuits is that if the grid goes down, they disconnect from the grid and they provide power to the occupancy. The batteries can be charged by either the solar or the utility. And what's interesting now is that IEEE 1547 2018 version allows the utility backup per utility agreement. What does that mean? It says the utility can talk to your batteries. And it can say, folks, it's 5 in the afternoon. It's the 10th of August. It's 115 degrees outside. We are really hurting. We need to get more electricity into the grid. Can you help us out? We're willing to pay you 20 cents a kilowatt hour. And the battery talks back to the utility and says, well, 20 cents is pretty cheap because I know that you're probably paying a whole lot more from other sources. How about 25? And that negotiation goes on back and forth between the utility and the battery backup pack, strictly based on the programming of the batteries and utilities, no human intervention. And within a few hundred milliseconds, sorry, they've reached an agreement and you're selling back to the utility. Doesn't this burn out your batteries? Well, we'll talk about that too in a while. The point is, new lithium batteries now are rated for a whole lot of thousands of cycles. And they are rated not anymore now is in terms of their overall megawatt hours of storage. And that is, you can store 10 kilowatt hours, you can discharge 10 kilowatt hours, and you can do that 3,000 times, 6,000 times. So then you're getting those 10 kilowatt hours a day for 600 days or more. And if you're using the full 10. So that's the new rating that they're putting on batteries, because that's what you do with your electric vehicle. You know, you charge it up at night and you use the electricity during the day. That's electricity, not just staying in those batteries waiting for for the grid to go down. It's being used every day when you unplug and go out and drive. So, what do we expect for a properly designed and installed PV system? Well, one, it should meet electrical design performance specs. It shouldn't leak if it's on a roof. No, I'm not talking about leaking electricity either. Better not let any water in. It shouldn't blow away. And somebody mentioned they'd sure like to know for sure how you prevent that. And I can tell you that we're pretty good at that here in Florida. Look at the hurricane area across Orlando, the photos of the various neighborhoods and the ones that have solar on the roof that are passing down with 4-inch long by 3/16-inch lag screws. They're the ones where the roof doesn't blow away because the screws that hold the solar down also hold the roof down. And a lot of the insurance companies didn't realize that until they started looking at the pictures. So there's no big deal to design it so it will not blow away. Thanks to the civil engineers and ASCE 7-22, it's a fantastic design guideline that gives you wind air, all the wind pressures that you might be looking for wherever you happen to be. Be nice if it looks nice, but then again, beauty is in the eye of the beholder. And believe me, if you've got a battery backup PV system on the front of your house, and after a hurricane, you've got cold beer and hot water and hot showers, your neighbors are going to be envying and realizing how beautiful that system is. So interesting argument on that one. Should last 25 years or more with minimum degradation. That's what we mentioned earlier. Typical warranties on the system should assist the utility if your region uses IEEE 1547 compliance. And so that's your properly designed system. So what are we going to need? Modules, make the electricity. Racking to support the modules. Proper method for mounting the racking. Lots of different roof styles out there, from metal seam to shingles to tiles of various sorts. Each one has a different way to mount, but they're all out there. People are building racking systems like there's no tomorrow. You have to have an inverter listed to UL 1741, because you need to convert your DC to AC if you're going to be grid connected. You need all code compliant wiring devices, all code compliant utility connections, rapid shutdown provisions. If it's up on the rooftop, you have to be able to shut that whole thing down so there's no electricity that gets beyond 1 foot from the array on the roof if you have a problem and the emergency responder wants to shut you down. And of course, you need a permit. That sometimes is the longest part of the whole thing. And you need this utility grid connect agreement. But these are things that the installer knows all about. And as soon as you sign a contract, they get going on the paperwork. So what types of straight grid connected systems are there? There are several different types. One is a string-fed inverter type system. The circuit looks like this. And what you notice here, I think everybody has had a course in electric circuits. Pretty hard to get an engineering degree without having a general circuits course. And you see, we've got modules in series. So modules in series, their voltages add, but they all have to be running at the same current. And if they're all going to be running at the same current, they all had better be the same model with the same output power rating. They all better be looking in the same direction, and they all better have the same amount of sunlight, no shading on one of them, because that will affect the performance of the entire string. All right, and the total voltage of them, open circuit, on a cold day when the open circuit voltage goes up, has to be less than what the inverter can handle. Otherwise, you burn out your input electronics on the inverter. But again, calculations are easy if you understand what you're doing. You got to realize these things, depending where you are, could get up 10 or 12% higher open circuit voltage than their standard test condition value. And you can determine that from the parameters of the module that are on the data sheet, the open circuit voltage temperature dependence, which is listed, and we quoted that in an earlier slide. So notice, though, we've got parallel strings. So therefore, each string has to have the same voltage also. Otherwise, if one has running at a higher voltage than the other, it's going to feed the one at the lower voltage backwards. So they both have to have the same voltage. And that automatically happens when they're connected in parallel like that. But they can have different currents. They just have to have the same voltage. All right, and as a result, those that one common voltage and the combined currents get sent to the inverter, where they are connected each string individually to make sure that each string is going to be performing optimally. At the output of the inverter, there's an AC disconnect, and that connects some way to the utility, oftentimes through the distribution panel, through a circuit breaker, but there are other ways, and we're going to look at how that can be done. All right, so that's string fed. Another kind is a microinverter system. Difference being that every module has its very own microinverter. That microinverter has all of the properties and abilities of the regular inverter, except it's rated at a lower power level. Typical microinverter power level ratings are 290, 320, 325, 349, and there's some up in the 400 range. And there's some microinverters there where they put 2 in a single package and 4 in a single package. But the point being that they are designed to operate with individual modules, and what that does is maximum power point tracking at the module level rather than at the string level or the array level. And this comes in pretty handy when you've got a rooftop that has 12 roof planes and you got modules all over the place, 2 modules on one roof plane, 3 on another, 7 on another, 15 on another. Microinverters are extremely useful for that kind of a system. Okay, notice how the microinverters are connected. They are connected in parallel. The meaning of that, the significance of that, and the importance of that is that the microinverters operate at a constant voltage, but they have the current varying. So they are current sources. Okay, instead of voltage sources, they are current sources, and therefore the currents of the microinverters add as they are added to the line. But they all operate at the line voltage, which would be 240 volts, because remember, the output of an inverter is AC. So here we've got coming down from the roof 240 volts AC instead of something like 400 to 600 volts DC, or in the case of a commercial installation, could be as high as 800 or 900 volts DC, or in a array field, out in a field somewhere, the voltage can go up as high as 1500 volts DC as long as it's fenced in. So we're looking here on the microinverter system, 240 volt AC, and each inverter adds some additional current, like an additional 1.9 amps or an additional 2.35 amps to the system. And therefore, if you they terminate a circuit breaker down in this AC combiner and monitor box. And so there's a limit to the number you can put in the string, but in this case, the number in the string is limited to the total amount of current. And typically, they're in strings that are terminated with 20 amp inverters, or 20 amp circuit breakers. So that means you don't want more than 16 amps total coming out of the modules in the string. Okay. In fact, I reviewed a job just before coming online here that the designer forgot that he could only have 10 modules in a string with an inverter he was using, and he had one string with 11. And so that one had to go back to the drawing board to get that fixed. So anyway, here's microinverters. So one other system we should be aware of, and that's the DC optimizer system, which is pretty neat. Because what this does is it does there's 2 advantages here. One is that you have module level optimization. In other words, each one has a maximum power point tracking. But then the output is a voltage, and so we're adding the voltages of these optimizers. Now, the optimizer has a maximum output voltage of 60, so that helps you determine the length of the string. And as these strings are in parallel, it means that every string has to operate at the same voltage. And the voltage of operation of the string is controlled by the inverter itself. And so once the string knows what voltage it has to operate at, the voltages of the various optimizers vary depending on the intensity of the sun shining on their modules. So those modules with the most intensive sun shining on them put out the most voltage, and those with less sun put out less voltage. That's because the voltage, the currents of all these outputs are the same. They're in series. Okay, so the voltages have to different, and power, of course, is current times voltage. So that's the difference for the optimizer system. They're pretty popular, not as popular as the microinverter systems, but they're out there and they work, and it's pretty clever design. And then the rest of it, the rest of the hookup once you're out of the inverter looks pretty much the same. So those are the three kinds of systems that would consider no matter what you're doing. But normally, if you have a solar field, a huge megawatt system, you're going to use straight string systems without any optimizers or microinverters, and much larger inverters, and 125,000 watts or larger. In the residential, though, the other two here are a little more popular. Another one that has some popularity is the system that has a string inverter, but each string has its own maximum power point tracker, so each string can be facing a different direction. And still, as long as all the modules in the string are facing the same direction, the individual string outputs will be optimized by the inverter because it has separate maximum power point trackers on its inputs. Okay, so next step, what are you going to do? Let's mount them. So let's talk about some structural design considerations. How are we doing for time? We got an hour and 10. Let's go. We got work to do here. I'm still kind of, usually my screen catches me if there are any questions. So again, don't hesitate to ask a question or want to clarify something. The worst answer you'll get is we're coming to that. I'm not going, in my business, my job here is to make sure everybody walks away feeling like they didn't waste their afternoon, feeling like they learned something, that they're glad they came. So whatever I need to do to make that happen, you just let me know, because feedback is very important. Okay, so how about mounts? Well, you start with the module, unless it starts with the inverter or something else, and as far as the design. The modules themselves have to be listed to UL 1703, that's the structural. 61730, 61730-1, 61730-2, these are international standards. But again, these are structural issues, and the 1741 is the electrical issue. Okay, and that's for inverters that have to have quality output to the utility, which we'll talk about later. But this is the modules. They have standards, and they have to meet these, otherwise they don't get their listing. And in addition to the electrical properties, they've got thermal properties, as we've mentioned, and they've got structural properties. Some structural properties, some modules will withstand 33 pounds per square foot, some 69, some 75, some with 3 rails will withstand 81 or so. So these are things you need to know about, and they are available in the module data sheets. So let's assume we have a module, okay? Let's assume it's 65.9 inches by 39.4 inches, 1.34 inches thick, and it has 18 square foot. Now, that's kind of a small one, but the process is the same. More typical area now is about 21 square feet, but as long as you know the area, then you can follow this procedure. All right, and this particular one happens to be able to withstand 113 pounds per square foot downward force and 75 pounds per square foot uplift force. Now, what's interesting about it is typically the uplift forces are the dominant forces. So the 113 downward is something you just never worry about. You're mainly designed for the uplift, the 75. Okay, but it's just the way they're mounted in the frame that they can withstand. The frame itself can handle downward force stronger than an upward force. But 75 pounds per square foot uplift isn't half bad, and that'll do the job for most of the jobs that I see on a daily basis, including down into the 175-mile-an-hour wind zones. So roof zones. Now we talk about roof zones, all right? And if you look in ASCE 722, it shows that they depend on the roof type, slope, and the dimensions of the building. All right? And in general, but depending on the roof type and slope, the following are true. Zone 1 is the interior and subjected to the least wind load. Zone 2 is at the edges of the roof and subjected to higher pressures. And Zone 3 is at the corners and usually have highest pressures. And there are exceptions where in some areas Zone 2 with certain kind of module configurations actually is subject to higher pressures than in Zone 3. But this is in general, and that's an important word in this particular sentence. These are generally the case. Zone 1 is the least pressure, Zone 2 is but more, and Zone 3 is more, sometimes 50% more than Zone 1, and sometimes even more if you've got things called exposed modules. Zone boundaries, they depend on this factor A, which have a definition. If you read it 10 times, you still don't understand what it means. It's 10% of the least horizontal dimension or 4/10 of the height, whichever is smaller, but not less than 4% of the least horizontal dimension or 3 feet. All right, now you see what I mean by reading it 10 times or more, but you just keep reading it until you understand what it means. And then you follow the rule, because A is how you define the zone boundaries. And we're going to do an example so you'll see. Okay, so moving on. You got to fit them on the roof, so we need a roof. They have to draw it to scale. And of course, there are a lot of different scales, but we're looking straight down at this roof now, perpendicular to the roof itself for this one. And of course, most of the roofs that you see you're looking down at the plan view, where you then have to realize that the plan view, that the actual length from eave to peak on the roof is a lot more than what would be seen in the plan view, which is simply a projection of the roof onto a flat plane, like on drawing board. So here's a roof, 51 feet, 9 inches. This would be a hip roof. 51 feet, 9 inches one direction, 19 feet, 24 feet, 8 inches on the edges there. And so you can calculate A, and it comes out to be 3.5 feet using that formula. So zone 2 is as shown in the picture. Zone 1 and zone 3 are as shown in the picture. Okay. So now, where we know zone 1, 2, and 3, used to be, before modules were rated at able to withstand really strong wind pressures, you tried to keep all your modules in zone 1. Now, sometimes you try to avoid zone 3 if you have an exposed or edge module, which we'll define later. But for the most part, you can put modules in all these zones and still put enough anchors on so they won't blow away. So with that module we just talked about, let's see what we can do about filling up this roof. All right. And one way to do it might be like this. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We got 24 modules there. Is that right? 6, 9, 11, 13, 15, 17, 19, 21, 24 modules. Okay. So now all we have to do is figure out how we're going to connect them or hook them up. So not electrically, but how are we going to attach them to the roof to make sure they won't blow away? So if we assume this roof has 2x4 trusses, then we're going to try to anchor our mounting brackets into the trusses. All right, so let's, by the way, noting what the fire code requires, 18 inches or 36 walkways at the roof peaks. This system right here may not be code compliant. You may have to lay that top row of modules in the portrait, in the landscape orientation rather than a portrait orientation to make sure you've got that extra 18 inches or 36 inches, depending on the fire code. The fire codes are mostly local stuff, so you in a lot of localities have their own tweaks of fire codes. So that's something you need to look at carefully. The dotted line there is the zone boundary A. So you can see that a lot of these are just in zone 1, but a lot of them, even more, are in a combination of zone 1, 2, and 3. And that's where we need to use weighted average pressures in order to figure out what's the module being exposed to. So let's do the math. But let's first determine, well, let's do the wind load on this first. Here's what you need to know. The mean roof height, the roof zone, the risk category, exposure category, escarpments, module size, roof slope, roof type, wind speed. That enough? Wow, that's a lot of stuff. But if we know that, then we can calculate the wind uplift. All right, the wind pressure. So what are our risk categories? Well, number 1 is structures representing low risk to human life. 2 is all structures not specified anyplace else, which means houses. And 3 is structures that can pose a substantial risk to human life, or substantial economic impact, or mass disruption of day-to-day activity or release of toxic or explosive substances, factories, stuff like that. So some of you've heard of this maybe before, but ASCE 722 has long definitions of these things, and it's all right there. And most residential are simply are number 2. And most businesses, shopping center, for example, would probably be number 2, but number 3 would be like a chemical plant or something. And number 4 is, your fire station or something manufactures toxic fuel. So that if something happens to it, it can be a real threat to human life. Okay. And one would expect that if you're dealing with the type 4 structure, you're going to have to be a lot more fussy and a lot more rigid in your design. Okay, so then you calculate the wind load, and there we go to ASCE 722. And you look in chapters 26, 29, and 30 for the rules. And, if you're really seriously getting into this, you got to get yourself a copy and read those chapters through, and then read them through again, and then again, until they start making sense, because there's some pretty fancy formulas in there. You think electricity is complicated. I feel lucky being an electrical engineer, because the structural stuff and the stuff that the civils have, some of the formulas in ASCE 722 are, a lot of them are based on empirical wind tunnel type testing, and they're pretty fancy. Fortunately, they've reduced a lot of it to tables, so you can still do contact, but then you have adjustment factors that you use. But we're going to do it, so you'll see. You determine the design wind speed, then you calculate this Q sub Z. All right, and this is in pounds per square foot. So this is a pressure. Notice it's proportional to the square of the wind velocity. So wind pressure is proportional to wind velocity square. That's important, because especially for windmills, because the force is equal to the pressure times the velocity. So that means that you're looking at the velocity cubed in terms of the wind forces. So that's even more interesting. But we just don't want this thing to blow away. All right. So once we have this thing, oh, wait a minute, we got KZ, KZT, KE. So we got to figure out what those things are. Once we've calculated that, then we've got a number we can work with for the wind load, depending on the particular zone on the roof. So the pressure itself is QH times KD times much more coefficients. But that's right in the SCE 722, chapter 29.4 through 0.2 through 0.7. All right, so that's just chapter 29 of ASCE 722. And QH is simply QZ measured at the height of H, like 15 feet, 25 feet, 60 feet. And these other coefficients, well, we need to figure out what those coefficients are. So let's put some definitions. By the way, with all this math and stuff, if you want to have a look at it, you are welcome to order up. Our host will be more than happy to send you a PDF version of these slides so you have all the math in them. And if you want even more details, there are some books out there that you can read that gives you the more details, like the National Electrical Code and the ASCE 716. And there's even a book by the guy who's talking to you right now that just came out called Photovoltaic Systems Engineering, 5th edition. And that gives you a lot of explanations of 11 chapters of why it works the way it works. So QH, we talked about what QH is, so we can go back past that. And what about KZ, ZT, and all that other stuff? Well, KZ is a table, and it all depends on the exposure and the height above ground. And you just look, it's a table lookup job. Okay, so in the tables in ASCE 722. And as you can see, these numbers, it's very convenient. So the way we do this, we simply have a spreadsheet that has a lot of conditional statements in it, or we tell it all this information, how high above ground we are and what exposure we are, and it automatically puts the numbers into the formula and calculates it. So if you have a properly designed spreadsheet, once you know the answers to some of these things, within a few minutes, you've got your wind load calculations for all of your roof zones. But this is the background of it. And like I say, if you do it, if that's what you do on an everyday basis, you don't do them one at a time. You build yourself a nice spreadsheet and that you can run through these pretty fast. All right, so what about the other Ks? Exposure, sheltered by trees and stuff. C, all cases where B or D do not apply. That's good. That covers a lot of stuff. So what's D? Well, that's unobstructed flat area or water surface prevail for 5,000 feet or more in the upwind direction or within. All right. Well, in other words, I live on the ocean here in Highland Beach, Florida. So I'm in exposure D. And my roof is 130 feet high in this condominium. So that's a pretty nasty wind pressure up on that roof that my cooling tower and air conditioner have to withstand. Okay. And so B, C, and D. No A, no E, just B, C, and D. All right. And B is most common as a downtown type thing, but C is if you don't have shelter and you don't have wide expanses of water. All right. So in fact, there are some counties where you're required to use C here in Florida. South Florida hurricane counties, you no matter what, you use exposure C, unless you're on the ocean where you use exposure D. And here's a note of what I just was talking about. So what about this other stuff? You learn a lot of Greek for one thing. Exposure coefficients, the GCPs. Well, they depend on the system exposure, the roof zone, roof slope, roof type, but they're in tables, lots of tables. All right, so here we have a hip roof with slope between 7 and 20 degrees and exposure B. So there's a table that gives us the GCP coefficients, and there's two of them, one for upward, one for downward. Okay, so you get a plus and a minus for the GCP coefficient. All right, what about the KZs? Here's the GCPs first. And this is where it came from, figure 30.3-2E. And you see that the downward coefficients are the same for every zone, 0.6, but they go up as the zones go up. And this is very specific, hip roof with a slope between 7 and 20 degrees in exposure B. Okay, anything else? You got a different table to look this up in. Once again, you can put these values in a spreadsheet, lots of conditional statements, if thens, or however you design your spreadsheet. But it all goes in the spreadsheet, so you don't need to look it up once you've got a reliable spreadsheet built. And then if it's a flat terrain, KZT, that T stands for terrain, that's equal to 1, otherwise it's not. KD is a sort of uniform structure like a house, and that's 0.85. Um, like if it's a silo, for example, you get a different KD value, but most houses have square corners and the KD is 0.85. Altitude less than 1,000 feet, K sub E. K sub E is the elevation coefficient, and so it actually decreases exponentially as you go higher and there's less atmosphere above you. It relates to the density of air at the height of the installation. So anywhere up to 1,000 feet, K sub E is pretty close to 1, but if you get up in Denver, somewhere like that, then you can actually get by with the lower value of K sub E because the wind is less dense, therefore there's less pressure when it blows on you. But then again, it also is a little harder to breathe because there's less density. For a roof height less than 30 feet, if the exposure is B, then K sub Z is 0.7, period. On the other hand, if your exposure is C, then your K sub Z varies according to a table. In this particular case, the slope is greater than 7 degrees, so therefore gamma sub E is 1. And since the area of a module is 18 square feet, gamma sub A is 0.7, again, looking at tables to give that information. So with 115 mile an hour wind speed, which is pretty common in New England and mid-country, wind speeds we're using here in Florida range typically from 130 to 175. But 115, if you evaluate that expression, you end up with 16.6 pounds per square foot. I wonder if I can move this. Of course, how nice. So if I take QH times gamma E times gamma A, I get 16.6 pounds per square foot. All right. So that's a very useful number because now we can start looking at the individual zones. And here's our GCP. Here's one of the pictures that the folks in ASCE were kind enough to allow me to show in this drawing. But this is an ASCE 7-22 and shows that GCP for the kind of roof we're using now depends on certain things. A hip roof, slope between 7 and 20 degrees, and it also depends on the zone. Here's zone 1, 2, and 3 for the positive coefficients, that's downward. But then for the upward coefficients, we've got zone 1 here, zone 2 here, and zone 3 here. And notice that the up from 1 to 10 feet, nice logarithmic scale on the horizontal axis here. Between 1 and 10, they're all at their highest values, highest magnitude. And then they go down between 10 and 100. So if we've got a 22 square foot module in zone 3, then you can see that we're looking at something like minus 2 point, what are we looking at? About minus 2.22 or something like that. Now, there's some question about if you have a row of modules, what's the area of that? And our approach is usually the conservative approach, and we take just the area of a single module in calculating this value. But it conceivably is allowed that if you have a row of, say, 5 modules with an area of 100 square feet, and they're mounted within, next to each other with a gap of less than half an inch, one could argue that it would be okay to use a 1.4 value for that row. But we like to be conservative in our work, so we all just take the module. Because then if you have one module sitting by itself, the rule applies to that one the same as it does to the others, except for that one module by itself will likely be classified by exposed and also have to be multiplied by another factor of 1.5. In any case, the tables are there. It's all there. You just need to have a reasonable understanding of why you're doing what you're doing. And here's your effective wind area. Um, and here's the definition, span length multiplied by the da, da, da. And again, you can read that because, again, the whole idea here is to show you that the methodology is there. And if you're seriously considering you want to do this, you're going to have to look at it again and again and a few more times because it's not necessarily simple. On the other hand, it's well defined, and it's something that gives you a good feeling that once you follow these rules, you've got something that's going to last for a long, long time. And you can go to bed at night and sleep confident that it's going to be there in the morning, no matter how hard the wind blows. So here's your final wind load determination then. 115-mile-an-hour wind when the QH gamma E gamma A is 16.6. Then you get your final pressure by simply multiplying that by the exposure coefficients. And that comes out in a nice little table for the zones. The downward pressure, 9.96 pounds per square foot, and the upward pressure going from minus 24, or the suction as it were, from minus 24.9 up to minus 38.18. All right. So this is our conservative approach. That we could conceivably use 92 square feet and come up with something small, and it probably would work just fine. But we'd rather let somebody else get blamed rather than us if it blows away. Because there's always tornadoes and anomalies like that that are a whole lot more complicated. And if you're hit by a tornado, that's anybody's guess what's going to happen, because those speeds get way over 200 miles an hour. But anyway, it's pretty straightforward. The bottom line is it's straightforward. A fair amount of numbers in there, but once again, once you get used to it, and once you build a decent spreadsheet, it's not all that complicated to come up with these tables relatively quickly. And once you have these numbers, then you can decide how you want to fasten it down, okay? So you might do it like this. You got the mounting rails, and we're just guessing with the brown spots, that might be where the attachment points would be. And you notice the whole idea here is trying to distribute the load. We could, for example, we're spacing 48 inches on the attachment points, but if we spaced 48 inches, every other truss would not have anything connected to it. So it's common practice in the industry to put the attachments like this for a truss-based system. And so we've got 2, 4, 6, 8, 10, 11 attachments on the top, 2, 4, 6, 8, 10, 12, 14, 16, 17 on the next row. Notice that we've extended beyond the end of the row on that second row, because if we didn't do that, we would have too much of a cantilever on those end modules, and there is additional pressure on those end modules. So that's something you don't want to do. So there is a rule about cantilevers. Again, like every manufacturer and all the real people will tell you what the rules are, and you pay attention to that. But notice the top and the bottom rows, the last attachments are within the confines of the array itself rather than having the outer ones outside. But the overhang to the end of the module where the clamps are is less than 18 inches. Typically, that overhang rule or the cantilever needs to be less, or 16 inches. I mean, generally 16 to 18 inches is the maximum cantilever. So once we've got the numbers here, once we've got an estimated, we think this might work, and it's pretty straightforward to do this. After you've done a few hundred or a few thousand of these things, you get a pretty good gut feeling for what needs to be done. Then you do the calculations, and here's what you come up with. If the 18 square foot module, top row has 54.9 square feet in zone 1, 35.1 in zone 2. So you do the zone 1 uplift times zone 2 square feet, zone 2 uplift times zone 2 square feet, total uplift 2592 pounds. Same exercise, middle row, total uplift 3676. Bottom row, same exercise, more square feet, 110. 6,071 pounds uplift. So now we divide, what do? We divide the total uplift of the row by the number of attachments. And what do we get? This gives the average uplift per mounting point. So top row, 236 pounds, middle row, 216, bottom row, 289. So now we got to figure out how far in do we have to screw in the screws in order to have 289 pounds pull strength. And, or the other way you can do it is simply use a manufacturer's mounting, which in fact is what is typically done. In the mounts, for example, one mount has an 804 pound or 1,004 pound limit, another is 1179, another one is 400, and so on. So depending on the manufacturer's data, you can either pick, make sure that you distribute your attachment points so that no attachment point is subjected to more than 236 pounds, or you can decide how far the screws have to go in. But normally the attachments come with their own screws, so it's a little bit easier. This is just saying this is what what comes out, but then you're going to buy some attachments that will meet the requirements of this pull. That's what it really boils down to. Okay, so if you have 5/16 lag screws, those are pretty common, but sometimes 1/4 inch are used, and for that matter, sometimes even number 14s are used. And the advantage of number 14s is less likely to split the truss. On the other hand, their pull strength isn't as high, and you need more of them. But 2 14s is probably generally at least as good as a single 5/16. So how far, what's the pull strength? Let's just take a look at some of the numbers. If you go to your wood, well, I got a reference here somewhere, safety factor of 4. Oops, come on back. Southern yellow pine, 5/16, so we take 332 pounds per inch. That's common down here, but if you're a Douglas fir or white spruce, the tables are there. And so this tells you what the pull strength allowable is for that particular kind of truss. And as you can see, for a 5/16, we got less than 1 inch of embedment into the truss to meet all of those previous withdrawal loads, 236, 216, 289. Take a look. 5/16 southern yellow pine, 1 inch is 332. So 1 inch into the truss and we're good. So what about the electrical design? Let's do electrical. There's your structural design. Hopefully that answered that question. So now let's do the electrical. And let's do it with microinverters, and let's do it with power optimizers, and let's do it with string inverters and see what the differences are for this same system. Okay? Everyone has its own built-in maximum power point tracking. And everyone, one way or another, incorporates rapid shutdown at the module level. And we'll get to that. Okay? Now, inverters have to comply with UL 1741, which is the Underwriters Laboratories test procedure. The standard it's based on is IEEE 1547/2018. Okay? And here's what it requires. It has to be good sine wave, less than 5% total harmonic distortion. Why less than 5%? Because that's about what the utilities are. That's the utility goal. And most of the good sine wave inverters are less than 3%. So that's not an issue if they meet UL 1741. And the are maximum amplitude specified for the various harmonics. Okay, so you got to not just have less than 5% total, but certain harmonics have to be small because they're more likely to interfere with other things, like the odd harmonics, even harmonics, and so forth. But anyway, UL 1741 covers it. If you have something that has a UL 1741 listing, you don't need to worry about the harmonics and stuff. This just tells you what UL 47 bases its approval on. For disconnect, It has to disconnect from the utility if the utility voltage goes too high or too low. In particular, if it goes to 0, you want it to disconnect. And if the utility frequency goes too high or too low, you want it to disconnect as well. Now, there's a provision here in UL 1741, or 15, sorry, IEEE 1547-2018 that says that if the utility frequency starts going down, no, please don't disconnect if you are a utility, because that's the reason that utility frequency is going down is because they're becoming overloaded. And the last thing we want to lose is 300 megawatts of utility scale photovoltaic. So as of 2018, you don't have to disconnect if you have a special arrangement with utility. Otherwise, you have to have this compliance. Anti-islanding, what does this mean? Well, it simply means that if there are other PV inverters, like here you've got, say, 20 microinverters on a roof or 40 or something like that. If one of them goes down and the rest of them are still running, then the other one is going to think the other ones, the one that goes down is going to think the ones that are still working are the utility. Now, fortunately, because these things are designed as current sources, the utility voltage is what synchronizes the frequency of these inverters. So therefore, if the utility voltage goes away, the inverter frequencies start drifting, and they drift so they're finally out of range and they shut down. That has to happen in a matter of a couple of seconds. Okay, so that's the anti-islanding. You can't think, your inverter can't think your neighbor across the street is a utility. And theirs can't think yours is either. So therefore, you need to make sure that, but once again, the utility won't let you hook up unless you have this provision. And the utility can control the options for grid support. That didn't used to be the case, but since 2018, now that's just fine. So let's do the design of the microinverter system. It might look like this. Okay, we saw that picture before. And here's the rules. You match the microinverter to the module. And normally what that means is you simply, it depends on the number of cells in the module so that you know the open circuit voltage and the short circuit current. The large majority of microinverters are designed to handle, this says 60 cell modules. That's some microinverters, okay, but the large majority will handle 60 or 72 cell modules, and this also means 120 up to 144 half cell modules. And bottom line is, if the open circuit voltage of these modules is less than 60 volts on the coldest temperature day, then you're good. Now the 72 cell will typically be very close to 50 volts open circuit at standard test conditions, which means no big deal. They are not going to go beyond 60 volts anywhere in the United States on a cold day. So they're fine. If you need a check, then you go to somebody who knows the formula or look it up in one of the books that has the formula. Rated microinverter output current determines the maximum number of modules per circuit. I mentioned that before. And common microinverter outputs are 1, 1.2, 1.35, 1.45, but there is also some at 1.58. And these are at 240 volts. That is different at 208, and they're also available at 208 volts for commercial installations. Now, since they rarely generate rated power, the microinverters can handle modules with power ratings up to 150% of the microinverter rating. So a 290 watt microinverter can easily handle and be connected and paired with the 420 watt module. No big deal. That's done all the time. And that's because the modules rarely generate their full rated power. Okay? So even 440 watts, it's not unusual to see that connection. So there's your rules. So now let's use the rules. Here's module. There's what the module has, and here's what the microinverter has. And you can see the yellow stuff matches. Open circuit voltage is good. Maximum power voltage on the module is 41.7. And the microinverter is perfectly happy between 27 and 45. The power range of the module, 235 to 440, yeah, we fit in there. The maximum that at the low temperature maximum power voltage of the module is 35.5 instead of 41.7, but that still falls nicely in the MPPT range of the microinverter. So we've got a good match here. But how do you compare? The module has a 2-page data sheet. The microinverter has a 2-page data sheet. Compare the numbers, make sure they match. Make sure the microinverter numbers are bigger than the module numbers in most cases, but sometimes you want well, no, you don't necessarily want, well, sometimes, no, there's never a case, I guess, where you want the um, module number to be bigger than the microinverter number. Well, yeah, the power, it's okay if the module power is higher than the microinverter output power rating. 290 watt microinverter means that's a maximum output power. Okay, so there's the matching. So let's take this 400 watt 72 module, 190 watt, 1.21 amp microinverter, put them on the roof, and let's have two 12 module circuits each, because we can have a maximum of 13 per circuit, because we have to have less than 16 amps total to a 20 amp circuit. So how would we do this? Well, we can do here, there's 12 modules, and here, well, here's 12 modules, and that's 14.52 amps for each circuit. That's good, less than 16. 9,600 watt DC array rating. Everything's listed, the microinverters, microinverter cabling, and all listed is all provided by the manufacturer. Cabling is special PV wire that can be open wire and up on the roof underneath the modules. They don't have to be in conduits. They are tough insulation that can withstand the sunlight and any other weather that might impinge upon them. They're fine, similar to the insulation on utility wires that are insulated. These are fed to a combiner box down at the ground level. Okay, so there we've got the roof all worked out. Now, what are we going to do on the ground? Well, we have to decide on the circuits, and here's the circuits. And now, what's this ground level equipment? Well, here's coming down from the roof. We have two 20 amp circuits. Okay, and that output goes to an unfused disconnect. And inside that combiner box with this particular technology, and other manufacturers, some of them do it slightly different, but here we are actually monitoring the output of each individual module individually to see whether there's any issues with performance due to shading or any other thing. And this is data that can go all the way to the factory, and somebody out there and who knows where land is looking at what your system is doing, and they can call you and say, hey, you might want to check module number 17 because it doesn't seem to be working the way it's supposed to. And you go see whether something happened to end up on that module with like a flock of birds came over or something like that. Might need a little hose. So anyway, then we've got a disconnect. It's sometimes optional, but National Electrical Code does require an outdoor disconnect. So if most of the equipment is inside, then you'll need an outside disconnect. And then you go, that to PUC means the point of utility connection, and there are a number of different ways to do that. All right, here's one. You can connect a backfed 40 amp circuit breaker. And this is NEC 705.12B32, called the 120% rule. And it simply says 120%, I'm sorry, the 125% of the PV current, and that happens to be 36.3 amps, and that quantity has to be less than that plus the bus bar rating, or plus the main circuit breaker rating, have to be less than 120% of the bus bar rating. Well, 120% of a 200 amp bus bar is 40 amps. And we know that the 125% of the PV current is 36.3 amps. So we got 200 plus 36.3 is 236.3, less than 240. So we're good. National Electrical Code says that. Okay, now you might think, my goodness, we're putting 240 amps onto a 200 amp bus bar, but that's not the way it works quite. Because the current from the PV is entering at the bottom, and that circuit breaker for this particular connection must be located opposite the utility. And for that, the current from the PV goes up the bus bar towards the current coming down from the utility, and in fact, it actually subtracts from the utility current, because now the utility current doesn't have to make it all the way to the bottom, as long as those bottom circuit breakers are being fed by the PV. So it actually takes part of the load off the bus bar as opposed to adding load to the bus bar. And that's kind of interesting. So in any case, here's your 120% rule. There's the numbers. 236.3 is less than 240, and so it's good. So that's one possible. But now, what if there's no room in that main disk, in that distribution panel for another circuit breaker at the bottom? Then what are you going to do? Well, first, this little note that the AC circuits are 240 volts, but what are you going to do if you can't hook it up like this? Well, there's other options. So let's take a look. One is a line side tap if the 120% rule doesn't work. And here's what that looks like. And that goes by 705.11, supply side tap. And connection will look like this. You got a fuse disconnect, which has to be service rated. And you tap in between the meter and the main circuit breaker, provided that there's wires there that you can connect taps to, because sometimes that's all in one panel, and that's just a bus bar between the meter and that main circuit breaker, and you can't do this connection. Oh dear. So then what might you be able to do? Well, we haven't ended up with our possibilities yet. Let's see what else might be possible. If you can't get to that line side, then you might use 705.12B33. This is called a load side tap, and it would look something like this. Let's say you got a 150 amp circuit breaker in that main, and you just can't get at the line side of that top 150 amp breaker. Then if you have in your panel where you can add an extra 150 amp circuit breaker, then nothing, that 150 amp circuit breaker in the panel says no more than 150 amps will be allowed to go into that panel without popping the breaker. Now the panel, the current that goes into the panel is determined by the loads on the circuit breakers, and it has nothing to do with the PV being up there. That tap up there simply means that the PV is going to have first choice at feeding those loads downstairs, and the utility picks up what's ever left over. Okay? And as long as the current in that wire between the two circuit breakers, 150 amp breakers, is not exceeded, then you're good. So therefore, even if you add some additional loads up on that top meter can, if that's a combination of meter and distribution panel, as long as the sum of the circuit breakers or the overcurrent protection from the PV plus the loads does not exceed the rating of the bus bar and or the rating of that feeder between the meter and the distribution panel, then you can do that. So lots of options. And in addition to this, there's even another 705.13, which involves using current transformers and power control systems, which is now becoming fairly popular. And that's there, we don't even have a slide of that, because that particular method is only becoming popular the last 6 months or so. And then we see a number of those now. So like I say, the important thing about here is to understand why this stuff is done the way it is, because the world is changing rapidly. And so as new methods come in, if you understand how the things work basically, and I have a pretty good understanding personally, I don't have much trouble adapting to new changes, as long as they're explained reasonably on how they're supposed to work. All right. So anyway, here's 3 different ways to do the connections on this. Now let's build another system with optimizers. Notice here we got series connected, same circuit. Here's your design rules. This is what the optimizers do. We talked to that before. Okay, and we're 20 minutes short of our finish time, so we want to go through here relatively quickly. The idea, once again, here is what's out there. If you're really interested, you'll want to read it again. I'd tell you that I've read through this stuff a whole lot more than once. On the other hand, I'm used to reviewing 8 to 10 sets of plans every day, so this you get kind of used to this stuff when you do that. So here's the rules right here. That's what the optimizers do. The optimizers have to be matched to the module short circuit and current and open circuit voltage and the module power. Circuits may have different numbers of modules. Circuits have a different, which is also true for the microinverters, by the way. Microinverters and optimizers strings do not have to have equal length. They do have minimum and maximum lengths, but they don't have to be equal. On the other hand, string inverters that go to the same maximum power tracking input have to have the same length. But even with a string inverter with multiple maximum power tracking inputs, you can have different lengths of strings. So that's the key, is every maximum power point tracking at the inverter level. Well, that's not even a general story, because here you've got the maximum power point tracking at every module here. Okay, but there's the optimizers. There are different sizes for different modules, and you have to match them up, and we'll take a look at that. It's generally a good idea the array power should not be more than 155% of the inverter rating. Okay, so matching module to optimizer. Here we go with an optimizer and a module. Open circuit voltage 49.8. Absolute maximum input voltage 60. Okay, we're good on the optimizer. Notice the optimizer is DC in and DC out. Okay, so we're looking at the optimizer input characteristics and the module output characteristics, because the module output connects to the optimizer input. Okay, MPPT operating range 8 to 60. Okay, that's important. Maximum power point tracking. Maximum module current, short circuit 11.75. So this one happens to be maximum short circuit module current is 10.36. So 1175 is more than that. We're okay. Look at the efficiency on this optimizer, 98.8%. Weighted efficiency. That's assuming some operate more and some less, depending on the exact output. But that's pretty good. That's not much loss. Maximum optimizer output current 15 amps, maximum optimizer output voltage 60 volts. That doesn't mean they operate as that, but if you're calculating wire size, you assume that it's going to operate as maximum current. Or using engineering calculation and the rating power of the modules, you can come up with a different number sometimes. And but these represent the maximum limits. And there can be, these are not necessarily exactly what happens when you deal with power, but we're not going to go quite that far into the process here. But in any case, this module, this optimizer, they work just fine, because the optimizer can handle anything that the module is going to hand over to it. And that's simply the the rule that the optimizer has to be able to manage whatever it gets from the module. Okay, so inverter circuit length. Here we go with circuits. So if the inverter says, okay, optimizer, we're going to work at 400 volts today, then you notice that since the output of the optimizer has to be more than 26.7 volts, then you need enough of them in the string to make sure that it's actually equal to 400. So that means you're going to need 15 in the string as a maximum, okay? On the other hand, that's if the output is 26.7, but we also know the output of the optimizer can go as high as 60, but if it does that, the current has to go down. All right. So if you have 24 modules, you can have two circuits of 12, 7,600 watts at 400 volts and 15 amps. Then what? Maximum power for either circuit is 6,000 watts. So there is a limit to power for the circuit in order to not exceed the current and voltage limits of the inverter input. Okay, 7,600 watt inverters, here's what you can have with it. So you can see how this matches up and with the circuits. And so now what else do we need? The modules and the optimizers, they operate independently. So the orientation and shading of modules, they can be different because each module optimizer combination operates by itself and is not dependent or affected by anything else in the circuit other than limitations in voltage or current in terms of maximum, minimum. But in terms of the voltage across that optimizer at the output or the input or the current, that is variable on a case-by-case basis for the modules. So the minimum number of modules in the circuit is you divide the 400 volts of desired operating voltage by the maximum voltage of the optimizer. And the maximum operating voltage is 60, therefore you have to round up. And so the minimum number is 7. So we got a maximum and minimum now. The minimum number here, we say we can have between 7 and 15 and be comfortable. And notice with the microinverters, we could go between 1 and 13 with that particular microinverter. But one module can be on one microinverter, and that can be a string by itself if necessary. Haven't seen that, but it could be if it had to be. But here, the optimizer does have this constraint of minimum string length. In this particular case, it's 7. But 7 to 15 is reasonable. That's usually workable. So figure out what circuits are. Same 400 watt 72 module, 15 amp maximum circuit because of the output limitation on the optimizer. Usually wired with number 10 because that's the way we've been doing it for the last 50 years, and people get kind of in a rut on that. But we can do a 13 and 11 module circuit. That's 24. Why do that? Simply because there's 13 here. Well, no, that's 11, isn't it? Well, 3, 6, 9, that's 11. And then if we put all the rest of them into another one, there's your 13. 1,400 volts each. And by the way, the inverter, if it sees that its power input is getting lower, sun is going down, it's able to lower its allowed operating voltage. It will sometimes change the input voltage in order to accommodate the intensity, because it looks at the total power coming in and saying, wait a minute, we can run at a lower voltage here because we're not getting a whole lot of current. So we design this on a typical worst case basis, maximum voltage, but the inverter can, if it wants to, decide to run at lower voltage, just to make sure it keeps everything running. All right, so here's your wiring. 9,600 watt DC rating. optimizer, an optimizer cabling, again, listed by the manufacturer, and they're fed to the inverter at ground level, and guess what happens there? Well, same thing. Here's your 320 amp circuits coming down, connecting up your point of utility connector. You can either do it that way. That's your 40 amps into 200 amps thing, and that's your B3 2 NEC 705.12 B3 2, and or the 120% rule, or you can use the line side tap, or you can use the load tap. So once you get to the output of the inverter, your interconnect to the utility have the same rules, regardless of the circuitry you're using. Okay? AC to DC ratio thing. In other words, if you have an output inverter, microinverter, rated at 290 watts, and you put it connected to a 440 watt module, how many annual kilowatt hours will it generate? Well, if there's minimal losses, then one would hope that it would keep on generating the number of annual kilowatt hours proportional to the DC input of the microinverter rather than to the rating of the microinverter. And so here's a little simulation that I did using NRL SAM, a 290 watt microinverter and various module ratings in the Miami area. Okay, and Orlando area, my mistake. And here's what you get. From 300 up to 440 using a 290 watt microinverter, it's a linear curve. So in other words, the output is directly proportional to the input DC power rather than the AC rating of the microinverter. So the whole idea of using a bigger microinverter, there are bigger ones, and yes, you will incrementally, very incrementally increase your output, but not very much, not very much at all. As you can see, otherwise this curve wouldn't be essentially linear. So and that's something that there's so many myths. I almost want to do a 2-hour lecture on the mythology of solar because there's so many myths, and I hope we have dispelled a few today, by the way. Now let's use MPPT at the inverter level, okay? Again, same rules here. And but you have to do a lot more calculations because here we are not, we're allowing these on the cold days, we're allowing these modules to get cold and that their open circuit voltage goes up. And when that happens, you can damage your inverter. So we need to do that calculation, okay? And also we need to know the minimum value of the maximum power voltage. And that can be as low as 85% of the standard test condition value. So it's nice to know the minimum value to use in your design because that determines the minimum number of modules in a string. Okay, so again, here's your design rules and considerations. And that again, once again, if you really want to get serious, you want to read this again and maybe even get some more literature to read. But if we have the same module that we had before, I think this is the same one. Anyway, then we look at the voltage extremes, and here's a formula that you use to do that. Okay, and you're simply using that 0.0028 is simply the temperature coefficient of the open circuit voltage, and you multiply that by the 45-degree temperature difference between the coldest temperature and 25 degrees C. So that's where that 45 degrees comes from for a minus 20 degrees C temperature, which is, you know, cold, but compared to someplace like International Falls, Minnesota, that's a warm day to go out skiing. So in any case, but notice the open circuit voltage goes from about 50 up to 56. So that's a 12% increase, roughly, maybe 13%. So a 15% increase, most places, is a reasonable thing, and 50 to 60 is more than 15%. So therefore, with the open circuit voltage less than 50 and an inverter input that can go up to 60 or 600, depending how many, what your inverter input is, the 15% figure is a reasonable first guess. Okay. So you get 10.7 modules to reach 600 volts. Therefore, you don't put in 10.7 or 11. You have to round down to 10. So your maximum number of series modules is 10. And now to get the minimum, you have to adjust the maximum power voltage, see what it goes down to. At standard tests, it's 41.7, and it goes down to 34.9 if you're at 65 degrees C. All right. Now, that doesn't mean the hottest temperature outside will be 65 degrees C. That's going to be the hottest temperature of the module when direct sunlight is shining on it. Just like in your car, it may be 100 degrees outside, but thanks to the greenhouse effect, it's a whole lot warmer. And any other thing that you touch something that the sun is shining, it's going to be hot. So 65 degrees C is not an unusually hot temperature for a module in a southern climate when the sun is shining directly on it in the summertime. So anyway, this VMP can drop pretty far, like here down to 34.9. So now we have to look at 245 is the minimum for the inverter that's being used here. If we divide 34.9, that means you're going 7.02 modules to do that. So we better make 8 just to be sure. 7.02 is that's close, and that'll work most of the time. But it's even better if you set your minimum at 8. And so 7 to 10, and that's not a very good range of modules in order to accommodate them in all this temperature range and still have them perform as necessary. So for the previous array, here we go. 7,000 watt, we're picking an inverter, and here's the 7,000 watt inverter. Maximum DC in 600 volts. Maximum power range is 245 to 480, so that works for the maximum power point voltage. Output current rate at 29.2 amps at 240 volts. So that means the design wiring sizes and so forth have to be based on 125%. That's 36.5. Okay. And the inverter output overcurrent protection, then it's going to be 40 amps. Okay. Now, if you had a 7,600 watt unit, which is also very common, by the way, then that's going to come out at almost exactly 40 amps. It's going to be 32 amps output, and 125% will be 40. So chances are, instead of 7,000, depending on the manufacturer, you might go to 7,600. But still, 9,600 over 7,600 is a pretty reasonable DC to AC ratio. 3 independent MPPT inputs, so that's good. You can have strings on different roof planes. But in this particular design, they're all on the same roof plane, so we're happy there. So therefore, you have to have a compatible rapid shutdown system. My goodness, it's over. These are my 2 grandchildren, 20 years ago. Even now, if we all do our part, they will appreciate it because it's their world that we're working for. Well, probably yours as well. I'm 81 years old, so I'm still working for their world. And it's 4. Anybody have any? We can use a couple of minutes. Our host is always fairly generous. He'll allow us 3 or 4 minutes if we have a discussion, any questions, comments. And here's the chat comes up with 2. Let's see what we got. Microinverter count, the amps don't change, so what limits the number of modules in the circuit? What limits the number of modules in the circuit is the maximum current that can come out of the microinverter. So if it's a 1.21 amp microinverter, then you have to divide 16 by 1.21, and that says your maximum can be 13 in the circuit. Okay, so it's the maximum microinverter current times the number of microinverters has to be less than either 20 amps or 30 amps, depending on what circuitry the manufacturer specifies for their overcurrent protection. And let's see. Oh, cute grandkids. Thank you, Maria. I'm sure they'd appreciate that. The one on the left was just down visiting 2 weeks ago with my great grandson, who was about the size of her brother in this picture. Uh, and let's see, spell the name of the program. We did that. Any other comments? Wind load design, we did that. How many panels can be strung together on one circuit? We got that. And again, if you're really seriously interested, there's work out there. I'm proud to say that last year Florida ranked #2 in the country in terms of overall PV installations, including residential, which is mostly what we do. And we're hoping to keep that up. People are starting to wonder what's going to happen, but the numbers are still good. Wall Street likes solar, and they understand how to do all this math about levelized cost of electricity. All right, so here's a note from the boss. How to get your the quiz, and so on and so forth. So let me say thank you to everybody. I hope you got your money's worth today. I think the program was run at a discount, but I tried not to discount the quality of the presentation. Because I'm interested in this kind of material. I'm going to wait. I'm going to monitor my participant list, and I'm going to hang on for a little while until, wait a minute, there we go. And until everybody's signed out, just in case somebody has a last minute question, I want to be able to deal with it. So. But just as a reminder, we're done. Program's over. And we're simply holding out in case anybody has any final questions or comments. And please fill out the evaluations at the end as well. They're very useful. And be specific if there's something you like or didn't like. We aim to please. I didn't spend 35 years teaching electrical engineering, wondering whether people were catching on to what I was talking about. I paid very close attention to my evaluations. Do the same here. And that's a separate form, by the way, that you find on the website, I guess. Okay, well, Mr. Facilitator, I believe we are probably ready to sign off here then. And there's a few folks still, I think, looking at what they need to do next. But meanwhile, I'm going to close the presentation and stop sharing. and say one final thank you to everybody who joined us today.